Before I start and dive into the slides, I just want to sort of set the context of this a little bit. And there's a great book that I highly recommend by a woman named Sarah Hagen, who towards a sustainable architecture, and she posits in this book that there's really like 3 levels of sustainable architecture, and the first one is the prerequisite, which is excellent performance. And sometimes she says that the buildings has to have good guts or good performance. And the second is that the building responds to external forces. And the third is that the building conveys and communicates on a humanistic basis sustainability. And we spend, as architects, a lot of times in the second and third category, and sometimes have skipped over to a large degree the first category, which is performance. And I know it's after lunch, but this first presentation is going to be very much about about performance and about this sort of vegetables before your dessert type of approach. So I hope you didn't have dessert. So with that, I'm talking about passive house and tall buildings. And I'll set the context first. Having sat through a number of these sessions already, I'm sure you've seen this slide, which is population growth that's coming and as we've experienced, and it's truly quite remarkable. And along with that is carbon, and how much carbon we're putting into the atmosphere. And basically, if we go unmitigated and we keep on this asymptotic curve, we are really going to be cooking ourselves literally and figuratively. So what we need to do is bend this curve, and it's something that's really a preoccupation, should be a preoccupation. And of course, someone else in this conference has shown this slide. A lot of that's going to happen within this circle. As many people live within this circle as outside of this circle, which is also quite remarkable. And once you've experienced the megacity that we're in, it's sort of a little bit more evident. So here's the megacities. We're right in here. I'm from that megacity, the first one, New York, and this is going to be a lot about some New York experience. So this is also interesting. So this is a graphic representation of various nations' carbon emissions. So this is the people from the U.S. are heavier, and it really shows here. But it really shows from a population point of view where the carbon emissions are. And when you compare that to megacities, it then becomes no surprise that when you really drill down into the numbers, New York is actually the most wasteful megacity on a per capita basis. This was National Academy of Sciences. So it's really an area where we have to address. This is what the problem is. Well, now, I'm just going to take a quick digression. In New York, like other places, there's really an acute housing issue. Mayor de Blasio, who's the current mayor of New York, has basically made a goal of doubling the amount of residential units that are produced. This is pretty interesting. Average New York yearly new residential unit production over the last 20 years have been about 20,000 new units a year. We're experiencing a population growth in New York. The number of new units right after the crash was 6,000, and in 2014 things got healthy again, 25,000, and then in the real boom years, 2005 to 2008, 30,000. So de Blasio is said to double the rate of 20,000. So we just finished building on the left, and we said, well, that's 500,000 square feet. It's about, 500 units, so it's 1,000 units if you have 2 of them. So the housing production per year in New York, in the 5 boroughs, needs to be this many towers. So it represents a lot of new buildings, new opportunity for savings. So with that backdrop, then we look at these charts, and this comes from some of the next several charts all come from the New York City Planning Office and Energy Office and so forth. So this was our emissions in 2005 when the Bloomberg administration started to really focus in on this, and really, you know, between these 2 segments, you see that's really where the opportunities are for energy savings. And, you know, honestly, we've done pretty good here. You know, just in 9 years, we've decreased somewhat the amount of emissions, and that is with the backdrop of a growing city. But this is where we need to get to realize the goals of the administration and help our contribution to bend that curve that I showed you earlier. So this is where we're somewhere here right now. That's where we're in 2012, and really the green line is what the built environment has to do. So then we looked at, like, okay, what are the opportunities in the built environment, and going for the low-hanging fruit in multifamily, which is what this is about. This number is quite astounding. Space heating is about half of that energy use. For office buildings, it's about 1/5, with cooling and plug loads, you know, making up about half. But if in aggregate, it's still a very large number. So we started looking at ways to address this issue. And there's a well-known technique out there called PASSIVHAUS. And what we looked at for PASSIVHAUS that was attractive was the fact that it has the opportunity to have such a great reduction in heating energy. So what is PASSIVHAUS? And I have to say PASSIVHAUS is, and I hope no one here is from the PASSIVHAUS Institute, is very poorly branded. It is actually active, and it's not a house, it's all types of buildings. But really what it is this diagram where, 19th century, a lot of fossil fuels, a lot of clothing, poorly insulated houses. 20th century, heavily reliance on mechanical systems, and 21st century, really dealing both the symbiosis between the envelope, solar gain, and a light touch on a very sophisticated mechanical system. So what are the principles? One, air tightness, very important. Super air tightness, very little transference of energy and in between, of air in between and of energy in between. Thermal bridge free design, extra insulated, really great windows, and then when you do take air in and out of the building, there's a heat recovery system. So it's like a thermos that has a very carefully regulated heat in and out. These are the basically the requirements, universal requirements for PASSIVHAUS in terms of performance. I don't, to me as an architect, I look at this and I say, well, what does this mean? I really have to put it into some context. So this is in comparison to a good solid housing type of project that we would do. The heating demand is 3 times our base case here versus PASSIVHAUS, 3 times. Cooling demand is pretty close. Primary energy, it's significantly higher, and 6 times the air tightness. So this is a good practice building, but you can see like there's some very significant differences. So PASSIVHAUS has started to gain globally. There's a few here. a lot here. They tend to be smaller scale, but there are some high-rise buildings, and we're starting to see in North America more and more passive house being done. So its applicability to high-rise construction, high-rise typology. Northern Europe, there is one China example, I believe it's here. And in New York, our friends at Handel Architects are doing the Cornell dorm on Roosevelt Island using passive house. This is topped out and going to be habited in about a year. So we started thinking, this is really a fantastic opportunity to drastically reduce the amount of energy use in buildings. We do a lot of residential high-rise buildings. We do a lot of affordable housing buildings. So it was like, well, this is a very good target. And but inevitably, every architect, every professional, any policy person, and even any developer who's asking themselves, how do I improve practice, comes across, and being the first one out, comes across the issue from pure development concerns of how much more is it going to cost, what's the increased risk, what does it do to my systems, what are the implications. So we thought we would apply to the New York State Energy Research and Development Authority for a grant, having the idea of if we could do a side-by-side analysis of a high-rise building that we were working on that had good practice versus what it would take to make it a passive house tower in all of its dimensions. We could really then, and have it peer reviewed and have it really done thoroughly, we can then issue this report, and at least it would open up and progress the conversation further. So we were working on this building at the time. It's a 2-building complex. It's in Jamaica, Queens, next to the railroad. It's a transit-oriented development. It has 3 floors of retail, a large setback, residential building above. This side is 80% market rate and 20% affordable. This side is the opposite. There's a church in between, some parking below grade, and it's sort of a normal, urban, complicated building. Here's some views. And some views. One thing, it's a RAINSCREEN system with individual punched windows and has a ratio, interestingly, has a ratio of wall to glass about a third. So mixed-use development, by the way, the study is really only takes into account this building and not that building. So we thought, let's compare this building to a passive house. So this is about the size, 55,000 square meters, 109 square meters of retail, 290 feet tall, 88 meters. And it probably wouldn't fit on the bag, that you have in terms of these other towers, but it's still significant. 450 apartments, 90 are affordable. I already talked about that. So and then in terms of its performance, it was LEED silver with a 20% reduction off of ASHRAE. So it wasn't a horrible building to start with. It wasn't a phenomenal building to start with. It was a good, I would say B plus practice. And that was the construction cost. Just to put it into some context, these are some other towers. This is the one I just showed you in Brooklyn, but window to wall ratio is 50 or 44. So this one already started with a little bit more solid and a little less glass. And here are the R values. So we then did about a 9-month study with consultants, really engineered it, with cost consultants, with contractors weighing in. It was peer reviewed. These are the things that we did in terms of the system. We improved the air tightness, additional insulation, thermally broken details, passive house certified windows, which are basically triple glazed and have thermal breaks. Ventilation with energy recovery, I'll show you that in a moment, and just various MEP system improvements. So again, this was where we started. That's what the passive house required in terms of R values. So you can see in our base case scenario, we weren't even insulating the slab on grade. Passive house requires that. This is a normally okay window that you get in New York. This is what a passive house window would be. The roof, pretty close. The wall, about half. So, you know, we had some work to do. So this was our original detail, and it was, again, a slab edge, basically a rain screen with insulation, vapor barrier, insulation on the inside, and then passive house design, a thicker wall, all the, you know, this is sort of, you know, insulation 101 in a way. It's like, you know, you put the insulation on the outside, then the vapor barrier, it's thicker. You know, that much more insulation was needed for the passive house. The thermal breaks needed to be, supports needed to be thermally broken, and the windows needed to be really good. This was modeled, you know, and clearly this is done correctly, where, you know, there's very little, you know, there's a very nice, clear definition between warm and cold, and it's well insulated and so forth. Interestingly, and this is a little bit of an aside, and this is where government can start to play a role, is that New York City has adopted a zoning deduction for thicker walls for extra insulation. And you basically, the first 8 inches you cannot deduct, but if you increase the insulative value beyond the 8 inches, you get the next, whatever you do increase it, the 8 inches are free. It doesn't count against your zoning floor area. So it's basically there to take away the disincentives for thicker walls, because otherwise that thicker wall would count against the developer. All the products that we looked at are available off the shelf today in the New York market, and they're just a little bit more expensive. But between the windows, thermal triple glazing, rain screen clips that are fiberglass, if it's a masonry building, they're standoffs. Thermal break for slab edges, we see a lot of expressive balcony type designs. For residential buildings, a lot of balcony design, and putting in this thermal break now is becoming more and more acceptable. Basically, we're removing the problem of heat transference between balconies and the space in between, and of course other details. This was the base case mechanical system. The air was brought in from the inside. There was a heat pump that went up to a cooling tower, and in the case of this, there was exhaust that was just basically taken out through the kitchen and toilet exhausts in the apartment. And then the revised design basically kept this outside location of the heat pump, but no outside air was introduced there. In lieu of that, additional risers were put in, and at the top, there's a heat recovery wheel. So fresh air is introduced from above, exhaust air is taken out from below, and in between, the air is preheated or pre-cooled. So this is what, again, the base case versus the passive house design, where we were, and then this is where we wound up. This is what we had to do to the base design to get it to be passive house. So air tightness, this is a prerequisite. You have to meet that air tightness, so it is what it is. Primary energy, this has to be there. And you notice in our design, we're less than what the passive house criteria required, but that's because we needed to hit this number. So in other words, you have a bulky, very dense, there's a lot of apartments and so forth that's using a lot of primary energy, but we're able to have less perimeter area and so forth. So these numbers are actually even better than Passive House, but this is what controlled, was the primary energy. So this is the reason we really did this research, was that we were trying to understand what the cost bump was, what the cost increase was, because of those initial slides, we were really looking for a way to get market acceptance of this way to do a building. So in this case, again, a peer-reviewed cost estimate and so forth, we had, there we go, basically a significant but modest capital cost increase. It basically turns out to be $9 a square foot or $90 a square meter. Over about $5 million increase over the project. The energy was basically a 14-year payback versus the base case, which again was a lead silver, 20% less than ASHRAE. So it was, if you compare that to code minimum, this number would probably be half of that. The highest increases in costs were for windows, air, distribution, and general conditions, and I'll get into that in a moment. And the highest savings were for heating, cooling, and systems reduction. So this was also part of the study, and basically working with the cost consultants and so forth. You see the biggest increase in the air distribution system. All those risers are more money. The below-the-line costs were really things like just risk essentially, and a little bit more time, and this actually finds its way in other places. The blower door test, basically Passive House, to get that very, very stringent air infiltration, you have to do tests around the whole building. That costs money. Contingencies were also increased. Cooling you see is less because it's more insulative. The domestic hot water was just an improvement to get to the Passive House energy requirement. No change, no change. The bridging was a little bit more, to good detailing. The exteriors assembly was basically more insulation, modest increase. Doors. General conditions, there was a little bit more time because of the blower door testing and just uncertainty. Heating, other architectural software, more design, more modeling. And then the biggest increase was basically the windows for the Passive House. So, it was good in that it wasn't like 20%. Anytime we introduce something to the market, we were very involved when LEED was first introduced into the marketplace, and there was like, oh, those buildings are 20-30% more expensive. So sort of taking out the fear factor and really trying to understand exactly where the cost increases. So it wasn't crazy cost increase, but it wasn't insignificant either. So there's a little bit in between. You're dealing with very highly, it's a very constrained economic type of building type, and the margins are very thin. So, a $10 a square foot increase in hard costs is not insignificant. So with that, sort of recommendations in the report. First is to strengthen local building codes. We talk, there's a saying, the carrot and the stick, to move a mule, you have to have a carrot to, incentivize someone, and a stick to beat them from the back. So a stick would be the codes. You have to make sure that there's always a increasing level of performance in codes. Carrot would be a incentive for zoning. We get more floor area, there's more better, quicker approvals and so forth. One of the things we found out was that there needs to be some financial, or could be some financial incentives for the windows. The air barrier QA, these blower door tests seem to be the area, because you're talking about so much surface area elevated on a building, that would have the biggest concern for actual training and performance and cost and really risk. So training around that and incentives to help support that activity would be important. There's just not a lot of people who understand Passive House out there. There's not a lot of energy modelers, and there's not really a lot of contractors. So basically educating the community is extremely important. Expand research to retrofits. After all, in most of these areas where New York or London at least, there's most of the buildings are built already, and they need to also, they're poorly performing. And then finally, encourage regional projects where, you can basically hold up an example and say, here you go, we could do it, here, we could, you can invite developers and building teams in to witness the actual end result and really take this research and move it into the next phase. Just finally, this was a team effort. As I said before, our sponsors were NYSERDA. There's a representative from NYSERDA here today. Raise your hand. And Roxel, the insulation folks, and the folks who make the thermal brake, they help support this research. It was about $140,000 US over 9 months to do the research ourselves. Dagger Engineering, SGH, the Passive House Academy, and Durham, who did the cost consulting. We're part of the team. And with that, I thank you very much.